Swayam Prabha. Digital India. Educated India.
So, last class I have discussed the response of step loading and how to get the maximum response. Then what is Duhamel integral, which will be required to get the expression for acceleration, displacement and velocity. Now today I will discuss how finally I will get the response vector, and then how we will use that response vector. So, as I already discussed that the expression of acceleration, velocity, displacement, time history can be obtained by using the Duhamel integral, and I have already discussed what is Duhamel integral, and now I will get the final expression of this response vector, that how we will get the response vector final expression. Okay. So, that is my but one thing, the Duhamel integral that is applicable for linear that single degrees of freedom system. So, now for here, as I know that it is mentioned that what is SD? SD is the spectral displacement, SV is the spectral velocity and SA is the spectral acceleration. So, SB or SD I will get as that is the U max, that is the maximum value of the displacement, that is your SD, that means the maximum response. So, I have already discussed the response of different cases, and from there how we will get the maximum value, that also I have discussed. Few cases I have discussed. Similar way you can get this value for other cases also as per your requirement, and then that will be your this SD will be equal to U max. Okay. So, and then SV, that is the your SB is equal to spectral velocity, that will be equal to U dot max, and that is equal to omega 0 SD. So, that can be say that PSV, and your SG spectral acceleration, this SA is the spectral acceleration, it is not XG, it is SA. Okay, SA spectral acceleration, that will be U double dot max. So, all the cases is maximum value. So, this will be omega 0 square into SD. So, that is equal to omega 0 into PSV, that is PSA. Okay. So, what is that? What is that PSV? PSV is the pseudo spectral velocity. Okay, it is pseudo okay. Similarly, PSA is the pseudo spectral acceleration. Okay, and U max is the maximum displacement. And omega 0 is the natural frequency. So, I have noted omega 0 is that your natural angular frequency. So, that is also natural frequency. From here you can angular frequency, from angular frequency also you can get the frequency, that also I have discussed. So, this is your omega 0 is the natural frequency, and so this way I will get the maximum value. So, I will get the spectral first I will get the spectral displacement, that will the Umax, and I have discussed how I will get the Umax. So, and then I will get the SB, that will also U dot max, and then that means we have to multiply SD by omega 0, and for SA spectral acceleration we will get the multiply omega 0 square SD. So, I have discussed that how we will get the Umax. So, the similar way you will get the Umax value here for this response spectra. So, this is actually the value that you will get for the response spectra, and so many you have to use the help of numerical integration that I have also discussed to get those expression for velocity, acceleration and the displacement time history. So, finally, I will get this is my acceleration response spectra, velocity response spectra and displacement response spectra. Okay. So, as I mentioned that in this, that if your t is equal to 0, if your t is equal to 0, then or the frequency in infinite, then your spectral acceleration is equal to PGA. So, that means if you look at the site 1 case, here the PGA will be around 0.45 or around 0.45. So, this is the PGA actually, this is PGA. So, this will be around, this is PGA, peak ground acceleration. Here it will be around 0.35. Okay, because at t equal to 0, that the spectral acceleration is equal to PGA. So, that means that this one is your PGA or PHA. Now, from here, this is my actual response spectra, acceleration response spectra. Now, from there, I will get the design response spectra for different motion for because it is a function of, as I mentioned, it is a function of damping ratio and natural frequency or natural time period only. It is a function of damping ratio and the natural frequency or natural time period only. So, here also this is the time period, this is your here. So, these are the design spectra. So, design spectra is somehow different to the actual spectra. Design spectra is more smooth and compared to actual spectra. And what is the design spectra are basically the average of several earthquake motion. So, it is the average of several earthquake motion. So, here you can see this design spectra is given for different types of rock or soil. So, for hard rock or hard soil, for medium soil, soft soil, these are the different design spectra is given for 5% damping ratio. These charts are developed for 5% damping ratio, and this is your natural time period. So, you can see this is actually your design response spectra, and this is design response spectra, which is more or less smooth. Okay. So, this is actually average of several earthquake motion. Now, here this SA by G, actually the design acceleration coefficient is treated as design acceleration coefficient, which is normalized with PGA. So, as I mentioned that at t equal to 0, that your spectral acceleration is equal to PGA. Now, if you normalize it with respect to PGA, then at starting point definitely the value will be 1. So, you can see that starting point, this value is 1. It start all the curves, they start from 1 because it is normalized with respect to PGA. Okay, and t equal to 0, your spectral acceleration is equal to PGA. So it will start from 1 and then it will follow this trend. Here also, if you smooth curve draw, this will be the similar type of response spectrum. So now why this curve is required? Because here this is my SA by G is the design acceleration coefficient normalized with PGA for different soil time with respect to particular natural time period of a structure. So that means from here you will get the value of SA by G with respect to a natural time period of a structure. Okay, so for different soil times and can be used to determine the design horizontal seismic coefficient and finally the design lateral force for the structure. So ultimately to determine or get the design lateral force that will act on a structure, you need this response spectra for different soil condition or different ground motion. So that means you have to predict this ground motion properly to get this response spectra so that you can use them for design of earthquake resistant structure. That means from here what I will finally get? I will finally get the design lateral force that will act on the structure. So that I will get from here. This is SAG is the design acceleration. From there I will determine the design horizontal seismic coefficient. From there I will get the design lateral force for a structure. Okay. So this is basically the use of these. I have discussed how these response spectra can be obtained, and then what is design spectra and what is the use of these SA by G value. Now I will discuss few other thing, that is the few other parameters. Okay, that is your frequency content parameters. That is the first. Another one is the predominant period, TP. The period of vibration corresponding to maximum value of Fourier amplitude spectra. So now if I draw the time period or period versus Fourier amplitude, I have also discussed how you will get the Fourier amplitude. Okay, Fourier amplitude if you draw, then the maximum time corresponding to maximum Fourier amplitude spectra is called the predominant period. So I can draw two different cases. So here the predominant period will be this one where it is maximum. This is TP. Similarly, another case which is a flat, but there also TP is same. Okay, so which indicate that predominant period provides some information about the frequency content. Okay, so different frequency content can have same predominant period. So you have two cases where they have different frequency content, but their predominant period is same. That is okay. That is the one observation. Now next one is get the value of Vmax by Amax. Vmax is the maximum velocity, Amax is the maximum acceleration. Okay, so that is you can see that is your PGA or PHA, peak horizontal acceleration. So that can be tell as a Vmax by Amax, maximum velocity divided by maximum acceleration. Now seed and Idris provide some average value which is for less than 50 km from the source. So different types of soil and rock, that this is the your Vmax by Amax value. So that an unit will be definitely a second. Okay, so this is rock, it is 0.056, for steep soil less than 200 feet or 61 kilometer, it is 0.112 second. For steep soil greater than 200 feet, it is 0.1384 second. So that means as the your that rock, for rock it is that this value is less, and you can see for steep soil it is more. Here it is given. So now another thing, that what is actually we can prove that Vmax by Amax is equal to that I can prove that Vmax by Amax, that is equal to your T by 2 pi. It is given T by 2 pi. How I can get that? Suppose if we have a, if we take that my displacement is A sine omega t, or ut you can say is A sine omega t, that we can represent them. So my u dot will be A omega cos omega t. Okay, and u double dot will be minus A omega square sine omega t. Okay, so I can write that Vmax. So here if I take that max, modulus of that V dot max, or I can write this is your Vmax, that is equal to AW maximum velocity, cos can be 1, that will be maximum. I am taking the absolute value. Similarly, u dot double dot max or A max, that is equal to, if I take the mod, it will be A omega square. So Vmax by A max, that will be AW by AW or A omega, or by A omega square. So this will be 1 by omega. So I know that your T is equal to what? T is equal to 2 pi by omega. So omega will be equal to 2 pi by T. So it is 1 by omega. So this will be T by 2 pi. Okay. So that's why this unit is the second. So now the next one is the duration of the motion. That is also an important parameter. So I have discussed there are three parameters. What is the amplitude parameter? One is the frequency content parameter, and in the last one is the duration of motion. So amplitude parameters, the major parameters are your acceleration, displacement, and velocity. And in amplitude content parameters, we have discussed the Fourier spectra, your power spectra, response spectra, and then now the duration of the motion. Now the duration of the strong motion has significant influence on damage due to the earthquake. So I am talking about the duration of the strong motion. Okay, and I have define what is strong motion. That strong motion is the motion which has significant effect on due to earthquake on a particular structure or anything where we have a significant effect. So duration of strong motion has significant influence on damage due to earthquake. A short duration motion may not produce enough damage if the amplitude of motion is high. If the amplitude of motion is high and it is in the short duration, it may not produce enough damage. On the other hand, the long duration motion with moderate amplitude can produce significant amount of damage. Okay, the duration motion is related to the time required to release the accumulated energy along the fault rupture. Okay, the duration of strong motion is related to the thus the duration of strong motion is related to the magnitude of earthquake. So that means as it is the function of the time required to release the energy, so that's why the duration of strong motion is related to the magnitude of the earthquake. The duration should be proportional to the cube root of the seismic moment. So we have already discussed what is seismic moment, m0. So that duration is proportional to the cube root of that seismic moment. Okay, so now how we will define the duration of this motion? Now the first one is the bracketed duration. So the time between the first and last exceedance of threshold acceleration, that is 0.05 g. So that time is called the bracketed duration. So what is that? So if you look at these your acceleration time history, we have two acceleration time history here. First exceedance of 0.005 g is here. Okay, is here, and the last exceedance is here. So the time in between the first and last, that will be treated as a bracketed duration. Similarly, here first incidence your exceedance is here and last exceedance is here. So that will be the duration of the motion or bracketed duration. Now another way it can be defined, the time interval between the points where 5% and 90% of the total energy has been recorded, that can also be treated as the duration of motion. Or it is also defined as it is equal to the corner period or inverse to the corner frequency. I have already discussed what is corner frequency. So it will be equal to the corner period, or that means the inverse to the corner frequency. So in different way you can define the duration of motion, but among all these things, this bracketed duration, this definition is generally or more acceptable, or we use that. Okay, so that means the bracketed duration. Now here we have a chart, we have a table. We can see that it is given for less than 10 kilometer epicenter distance. If the magnitude, what is the relation between duration and the magnitude? If it is a 5 magnitude, then for the rock it is 4 second, and for soil it is 8 second. For 6 it is 8 and 16, 7 it is 16 and 32. For 8.5 it is 43 for the rock side and 86 second for the soil side. Okay, so this is our duration of the motion. And the next one that I will discuss about the estimation of ground motion parameters. Okay, so till now I have discussed the what are the different ground motion parameter, then how we will measure them. Now how we will estimate them for a site. If I want to estimate what will be the PHA of that particular site before a design, how I will estimate that. Okay, so suppose in a site I want to estimate that, or I want to design something, then what would be PHA or PGA I will consider for that site. Similarly for velocity also, what value I will consider. So and other parameters that I have discussed. How we will estimate them, that I will discuss in this part. So now the first one, the estimation of peak acceleration, because we have discussed the estimation of peak acceleration, estimation of peak velocity. The first theory that is proposed, that Cornell et al. 1979, they developed a relationship for PHA, peak horizontal acceleration, considering earthquake data of magnitudes m equal to 3 to 7.7 at a distance of 20 kilometer to 200 kilometer in the western United States. So this data is based on the data. What data they have taken? They have taken data for the earthquake data in the western United States for magnitude 3 to 7.7, and the distance of those data is at a distance in the range from 20 kilometer to 200 kilometer. And where is which magnitude? It is the moment, it's a magnitude, though it is not mentioned which type of, so data of magnitude is mentioned. So when its magnitude mentioned, generally we consider it is a moment magnitude. Okay. Otherwise, this magnitude will be specifically mentioned which type of magnitude is used. If it is not mentioned, then we will consider it will be moment magnitude. Okay, because that is the magnitude widely accepted and more popular for engineering design. So what is the expression? This, it is ln pha gal. It is in gal. Okay, that is equal to 6.74 plus 0.859 m minus 1.8 ln r plus 25. So next time I will give you only the expression. I will not read because these expressions are easy to understand, but I will give you the history behind to develop those expressions. Okay. So here what is r? R, m is the magnitude, r is the closest distance to the zone of rupture in terms of kilometer. Okay. But remember that these data are site specific. It is for Western United States only. Now, suppose if you are designing anything for a particular location, you should use the data of that particular location where you want to estimate that Emax, if you have those data. Okay. Otherwise, you can use the available correlation, but it's better to use the data of that particular location and then develop the expression for to estimate these properties. Okay. But first general type of expression which was proposed by Campbell 1981. So they developed the attenuation relationship for mean PHA for site within 50 kilometer of the fault rupture. So that is within 50 kilometers. So that means that expression with this is given, it is applicable for within 50 kilometers from of the fault rupture in 5 to 7.7 magnitude earthquake. Okay. Because why it is in general? Because worldwide data were considered to develop this relationship. It is not a site specific. Worldwide data is considered. So that is in terms of a general type of expression. But today it was developed is 1981. So this is a very simple expression. But today we have more advanced expression where so many effects are being considered. If you see this expression here, only the magnitude and the your r, I mean closest distance, only distance and magnitude is being used. But now in this 2023, more advanced relationships are available, but so many things are being considered. But as it is the this is the old developed theory, that we should know how these things are coming. So now here it is applicable for your within 50 kilometer from the fault rupture and for magnitude 5 to 7.7, and worldwide data were used. This is the expression. So it is in terms of G, ln pH G, and m and r. Exp means E. So where m is the local magnitude if m less than 6. That means Richter local magnitude. But if m is greater than 6, then it is surface wave magnitude. Remember that. So that is the things you should remember if you use this expression. Okay, and closest distance to the fault rupture is r, which is in terms of kilometer. Now next equation that I will discuss about the equation proposed by Idris. So that is the relationship of PHA for rock site. Okay. And one more thing, here it is given sigma ln PHA equal to 0.37. What is sigma? It's a standard deviation. Because here this expression is giving you the mean value of the PHA. Mean value of the PHA. And standard deviation means if standard deviation is very low, which indicates that all the other values, the data that they have taken from those data, they have proposed this expression, and if you use this expression you will get the mean value. So that means all the data are very close to the mean value if your standard deviation value is very small. So, this is the standard deviation. So, later on I will show you one example where you will find how I will use this standard deviation in later on. Okay. So, now the relationship for PHA for rock site is given by using these expression. Okay. So, these expression I am not reading, because this you can see. So, only the what are the important thing that I will discuss. So, I think this is the MW, this here moment M is the MW, moment magnitude, and previous case it was for less than 6 it was local magnitude, and greater than 6 it is surface wave magnitude, and the first case it is only magnitude is given. So, we will consider it is also moment magnitude. So, here also two expressions are given if moment magnitude less than 6 and moment magnitude greater than 6. So, here also R is the closest distance to the zone zone of rupture, and then your standard deviation of ln PHA will get two expression, one for MW less than 7.25, one for greater than 7.25. And this is first expressions are for rock site, and second expression lower expression is for soil site, that is soft soil site developed for based on acceleration of rock site and amplification ratio. Okay. So, now these are the expression, and again two expressions are there, but here no standard deviation value is being proposed. So, it is mentioned that due to the limited data available for soft soil site, same standard deviation terms as proposed for rock site are also suggested for soft soil site within a limiting value of 0.6 G. So, that means the limiting value, it cannot exceed a value of 0.6 G, but you can use the standard deviation of the rock site. So, the source is given from where these expressions are taken, these sources are given. So, now this way we have several attenuation relationship, so are proposed for all the parameters. So, in the next class I will discuss all these relationships, and I will discuss about how to estimate that ground motion parameters. Thank you.